In the previous lecture, we have seen how the life cycle of an actor looks like, that it starts, that it may be restarted, and that it finally stops. This life cycle has implications, and we'll see two of these in this session. When we look at an actor from the outside, the only thing we can see about the life cycle is the transition it goes through when it stops. The only actor which can observe that another actor starts is the one which creates it, and as soon as it has the actor ref in hand, the child actor has at least been alive for some period of time. Other actors which learn of the existence of this actor by getting the actor ref know also that at some point in time the actor was alive, but in order to find out more, they need to exchange messages with it. We have seen that restarts are not externally visible. The actor ref stays valid, and if the restart is successful, the actor will handle messages afterwards again, meaning that an external observer cannot really tell if an actor was restarted or not. The only thing which can be seen is if the actor stops responding. But what does it mean if we don't hear back from somebody we call? It might be that the other end is just not there anymore. It might also be that our means of communication are broken. To remove the ambiguity between an actor which has terminated and one which is just not replying anymore, there exists the feature called Death Watch, which is a means to monitor the life cycle of an actor. Any actor can register its interest in monitoring the life cycle of an actor for which it has the actor ref by calling context.watch and giving it the target actor ref. When the target actor terminates, the actor which monitors it will receive a terminated message. Within this message, the actor ref is given of the target which it was that just terminated, so that the monitor can disambiguate between multiple actors it might be monitoring. The meaning of this terminated message is that this actor will not receive any further direct communication from the target. Of course, messages might still be en route if they were sent via different intermediate actors, but direct messages sent from the target to the monitoring actor will have been received before the terminated message, if at all. The DeathWatch API consists of two methods which are offered on the actor context. Watch, given a target, will register that we want to watch that target, and unwatch, on the other hand, will remove this registration. Akka takes care that after you called unwatch, the terminated message for that target will no longer be delivered. This holds true even in the case when unwatch is called at the time during which the actor is currently terminating. There is no race condition here. The third piece of the API is the terminated message itself. There are a few things to be noted about it. First of all, terminated is a special message. You cannot create it yourself, hence it is declared private except for Akka. This prohibits your code to use the constructor or the companion object's apply method. The main data this message transports is the actor ref of the actor which has terminated. But there are two additional bits of information. First of all, whether the existence of this actor could be confirmed by the system. And the second gives information whether this message has been synthesized by the system, as we will learn in the next session. I'll explain the first of the two flags with a little drawing here. Let's say we have one actor here, the watcher, which wants to watch another actor here, the watchee. Let's make up some words. If the watch message is delivered while the watchee is alive, that registers just a callback for later, so to speak, for when the actor stops. During this process, the terminated will be sent. And in this case, The system knows that the actor has existed because the actor itself sent the message. After an actor stops, its ref might stay there, but the actor itself is completely gone, removed from the system. So, if the watch comes in at this point, then the reply is generated by the system when it cannot find the target. And in this case, the flag is set to false, because Akka does not know whether this actor has ever existed. The actor ref could, for all intents and purposes, have been faked. Now that we know about the data which are contained in a terminated message, there are two extra pieces of information here. First, it extends a trait called auto-receive-message, which is an Akka marker trait, signaling that terminated messages are handled by the actor context especially. The reason for this is that the terminated message must not be delivered after unwatch has been called, and what this also means is that terminated messages cannot be forwarded. The last piece of information here is that terminated is possibly harmful, and we will see later what that means. Let us now see how we can use this feature. The first place where we try it out is the getter from the link checker example, which has been used throughout the last weeks. This getter retrieves a body of an HTML document from the web somewhere, extracts all links, and then it used to, after sending back the links, send to its parent a done message. This can be removed. In this case, we just stop ourselves, and in case of failure, we also just stop ourselves. Because the purpose of the done message was to serve as an end of conversation marker so that the parent knows when the getter is done. Using deathwatch, that is no longer necessary. Once the getter stops, a terminated will be delivered, and that serves the same purpose. Before we can look at how we need to modify the controller, which was the parent, if you remember, there is one more thing we need to talk about. We see here, and we have seen, every actor is created by one other actor, its parent. That also means that every actor can be the parent to possibly many child actors, and the context keeps a list of all the children. You can access it by calling context.children, which gives an iterable of actor refs, or you can also query it by taking a name and asking, does this child exist? And then you get back either some actor ref or none. The list, which is kept by the actor context, follows very clear semantics. When you call context actor off and the call returns, the child has in the process been entered into the list. As soon as the child terminates, it will tell its parent, even if you do not use deathwatch, and the parent will remove the child from the list. If you do use deathwatch, then that will have happened before you receive the terminated message. This is important because at any given time there can be only one child of a given actor which has a certain name. If you try to create another child with the same name, then you will get an exception. The reason for this is precisely the children list. Actors are identified by their names, hence they must be unique. Now we can finish the modification of the relationship between getter and controller using deathwatch. First of all, we install a supervisor strategy. We use a one-for-one strategy, and in all cases of exceptions, we say restart, but we only do that 5 times. Once the getter has failed 5 times, it will be stopped. The second modification is that we do not need to keep our own list of child actors. We had a map in this actor. Instead, we apply context watch to the result of context actor off here, which registers our interest in the terminated message. And when that comes, we just check, was that the last getter which just terminated? And in that case, we send the result to our parent. If you remember, There was an overall timeout which we wanted to set. And once we get this received timeout here, we used to tell all children to abort by sending them a special message. We can replace that now. First of all, we use context.children, and then we just use context.stop to stop them, which will result in us getting the terminated message here. There is one other thing which is new in this actor, and that is the use of context.actorOff with just one argument. Normally, we used a name, and it is always a good idea to give actors good names so that you can identify them, for example, in log messages. But since names need to be unique within an actor, it might be cumbersome to generate them such that this holds. If you do not specify a name yourself, Akka will choose one, and it will start with a $sign. So if you ever see that, that is the result of not giving a name here. This part of the namespace is reserved for these internal names so that they can be guaranteed not to clash with anything. Hence, you cannot create an actor whose name begins with a $sign. The previous example demonstrated the use of Deathwatch as an end of conversation marker, but it also has other uses. For example, to fail over. In this example, we have a manager actor which is supposed to connect to some database. It starts out with the prime, where it creates an actor for some database. It watches that one, and it will use that one. The code is, of course, not shown here. Once that has a fatal error and terminates, this case is handled, and we become the backup configuration. And in here, something else could be done. For example, connecting to a different database or storing updates in memory until the main database comes back online. You can implement any strategy you want. So far, we have looked at the consequence of the actor's end of life cycle. Now we will investigate what follows from its ability to restart. For this, I will use a small actor hierarchy. Let's say we have an actor named Top here. It has child actors A and B. And they again have child actors A1, A2, and so on. Child actors and their state are considered to be part of an actor's state, which is accumulated during its lifetime. Hence, during a restart, children are affected. They are either recreated or restarted. This means if, for example, this actor is restarted, nothing else happens. But if this actor is restarted, this whole subtree is affected. And if Top was to be restarted, then the whole tree would be affected. Assuming an equal distribution of failures in these actors, it is already obvious that those at the bottom here will experience most restarts of all. The purpose of a restart was to reset the actor to a known good state. This means that all changes the actor did to its state will be lost during a restart. That was the purpose. But what if these changes are important? What if they are needed for the function of the system? Then they need to be recreated upon a restart, and that can be a very inconvenient operation. Therefore, it is desirable to do that as rarely as possible. From the observation that the bottom actors will be restarted most, it immediately follows that the more important the state and its changes are, the higher up in the hierarchy they should be kept. But there is one thing more which we can do. In addition, we can make sure that we delegate risky tasks down the hierarchy to have them performed at the very bottom. And if something which is risky goes wrong and causes the actor to restart, the effect that will have will be rather localized instead of throughout the whole hierarchy. This is called the error kernel pattern, and it is one of the reasons why the application of the actor model in Erlang was successful. Therefore, akka goes one step further. You have seen that in akka this supervision is mandatory. It is not optional. So in akka you are forced to create these hierarchies. When we look at the full example of the link checker from last week, we see that intuitively we apply this pattern. The receptionist is at the peak of the hierarchy, and it has the important state, which is which requests are outstanding. And the getters, which are exposed to all the difficulties of parsing input from websites, for example, are right at the bottom, because they are most likely to fail. Using the features of supervision and deathwatch, we can make the receptionist and controller more resilient by using the terminated message to react to unforeseen failure. Doing that is quite straightforward. First, we install a supervisor strategy. There is a prefabricated one, the stopping strategy. For any failure of any child, it will just issue a stop command. The second modification which we need to do is that we need to register for deathwatch. There was only one place in the receptionist, in run next, where we then need to call context watch to watch the controller before we send it the check message. The last modifications are found in the running behavior. If we get a successful result back from a controller, we now need to stop it. And before we do that, we call unwatch so that we do not get the terminated message anymore. The next thing we then do is, as usual, check whether there is something in the queue and run it if so. If a controller terminates without having sent a result, we will get the terminated message because we watched it. In that case, we generate the failed result for the client here, and then we go on to the next job. In this case, we do not need to check the actor ref for which we get the terminated message, because at any given point in time there can be only one. This is the reason why we use unwatch here. The controller which successfully completed its mission is no longer of interest to us. The terminated, if it is received, will have come from the next one. Apropos, what happens if we do not handle terminated messages? I still owe you an explanation for why it extends the marker trait possibly harmful. Let me show you how these two are related. But before we can go there, we need to look at one more thing first. What we have learned so far was that actors can only communicate with other actors if they know their actor ref. Taking a step back and imagining not abstract actors, but a room full of people. This corresponds to pairs of people talking directly with each other, or groups forming which send themselves messages in a circle, for example. But if you have a lot of people in a room, there's another possibility. You can shout, and then everybody who wants to listen will hear what you are saying. The same concept exists in akka, and it is called event stream. Publishing messages to an event stream is like sending them, but you just don't know to whom. You're sending to an unknown audience. And all actors in the system have the ability to listen in on certain channels. The API for that is rather simple. Publish has the same signature as tell. And in the end, it does the same thing. Once you publish an event, everyone subscribed to that type of event will get it. To subscribe, the subscribe method takes the actor ref, which wants to receive the notifications, and the topic in the form of a Java class object. These classes are similar to Scala's types, but they're given by what the Java virtual machine supports. So the types you can express in this system are less powerful than Scala's. Still, it's very useful. For example, looking at a log event trait, This might have concrete subclasses, from debug to error, for example. And if you say class of debug, you get the debug class object, and if you subscribe to that, you will get all the debug messages. If, on the other hand, you subscribe to the log event class, you will get all of these. An actor can also unsubscribe from a particular topic or unsubscribe completely from the event stream. This is just a small example which shows how this looks like in code. Every actor system has an event stream. It is therefore accessible by saying context.system.eventstream. And this listener subscribes itself to all log events, which it will then get in the receive in the behavior. And in post-stop, it is good style to unsubscribe from all events. Armed with this knowledge, we can now look at what happens to unhandled messages. The actor.receive type is a partial function, which means that for any given input, it might not apply. Those messages which do not match are called unhandled, and they are passed into the method with the same name. It accepts any, and you can override it, but the default behavior is that it is matching on the type, and if it is a terminated message, then a new death pact exception is thrown. The default supervisor strategy will treat this death pact exception in a way that it responds with a stop command. This is inspired by the Erlang model of linking two processes. The intention is, if I am monitoring another process and I do not specially handle the terminated message, then what I want is to terminate together with it. All other unhandled messages are published to the event stream as unhandled messages, and as I've shown you previously, you could, for example, register a listener to log them if you want. In order to demonstrate this feature, I have modified the main program of our well-known link checker to include the context.watch for the receptionist. The reason is that the whole application exists only to support the existence of the receptionist, and it has no purpose once that has died. And you see, simply not handling the terminated in here will do what is commented. We signed the death pact with the receptionist. In order to see this in action, we need to make it fail, because otherwise this behavior will not be demonstrated. So let me hack in a bit here. This is a crude way to make the actor not respond, but it will serve its purpose. Running the application yields the well-known failure for the first one, and then we have 2 successful retrievals. But on the third one, the controller will not respond, it will just stop itself. And there we see the application gets monitored actor receptionist terminated, and then it shuts down. Feel free to experiment with this by inserting, for example, probabilistic failures throughout the hierarchy and see how supervision takes care of things.